My name is Encarni. I'm the current head of salt astronomy operations, and I spoke to Ketchel about it when she invited me to talk about what I do every day. So for me, this is really good fun and my passion. So if I get carried away, or if I'm not sure where to pitch it, so if I'm talking nonsense, not making myself very clear, just please put your hands up. If you want to interrupt, let's make it easy. It's meant to be fun. And does this work? What am I doing next? Okay, here we go. So SALT telescope, this is inside the telescope, I'm sure you already know. So it's a very, very brief introduction. 91 1-meter segmented mirrors. So each one of them is about this tall. And if you haven't been to Sutherland to have a look at it, please do, because it looks good in the pictures. It looks even better in real life. It's really big and impressive. And they built it for me, so it's really great. The thing about SALT that I'm sure you also know is that it's fixed in altitude. It makes it a little bit quirky. So it means it's always kind of fixing, can only observe things that are in the annulus in the sky, and we track them as the Earth rotates with the tracker at the top. Most of the instruments that I'm going to be talking about are sitting at the top, except for the high resolution spectrograph that just sits through a fiber. It goes down to under the telescope, the basement you don't see there. Where is SALT? Well, the headquarters are in Cape Town. One of the questions I always get asked is where are you based? I'm actually based in Cape Town, but the actual telescope is in Sutherland, as I'm sure you all know. Why Sutherland? Because of the dark skies, and I like that picture. It really illustrates just how dark the skies are. Also, we don't have strong seasonal weather impact. So it means that SALT can remain open all year round, while many telescopes have to close because of monsoons. That's a big advantage for us. And if you don't believe me that it's really dark, there's a really recent study, and there we are. We're fourth, like really one of the best sites in the world, even better than Mauna Kea in Hawaii. In terms of darkness, not with mediocre side in terms of seeing, but there's us, the South African Astronomical Observatory, and there's Mauna Kea over there. No volcano. After us, much brighter skies than us.
Parallels, darkest.
Yeah. Sorry, the font is there's too many telescopes, so the font is a bit difficult. How does that work? Well, researchers apply, because of the quirky type of telescope it is, right? We can't have everyone coming and observing at the telescope, so we take the data for everyone. So researchers apply for time on SALT using our software that Christian wrote. And they give us a science case. What do you want to do? What do you need the time for? Then they get reviewed by my team, in terms of whether there are any technical issues. Then we have also scientific reviews. Is this worthwhile doing? And then they get granted time. So they get allocated a time and they get allocated a priority. How important is this observation? Must I stop everything and observe? That's a 0. Or is it just a queue filler? I can do it when there's nothing else to do, which is priority 3. And we do get oversubscriptions. Some are unfortunately rejected. So then researchers that are successful take the time, and then they split it into observing blocks that we can observe at the telescope. They tell us everything we need to do with the telescope to get their data. All those observations are in a queue, and they stay in that queue until we either observe them and accept them, or the semester ends. So we do this twice a year, these calls. And then the SALT astronomer and the operator, as I mentioned, we go to the telescope into work shifts of the week, and then we take everybody's data. So what happens to the data? It's transferred immediately to Cape Town. It is put through what we call a pipeline, so some basic analysis is done. And then the people that apply for them, the principal investigators or PIs, are notified immediately by email that they got data from SALT. They know where to go and where to get it. They can even get faster access as soon as we've taken the data if it's needed. But normally most people are happy with the morning after. We have a very efficient and responsive SALT helpline. We're very proud, and Christian's very active on that. And we have also a night summary. Every night we write the summary of how the night went, and that ends up in a blog post. together with some random posts and sometimes some technical information about various projects we're working on those blogs. The data itself, we hold it also, we keep it in the SALT data archive. And once it becomes public after whatever period of time, other people can access it as well. And then it's accessible through the SALT data archive website. So anyone can go and check what data is available for SALT. It will give you all the public data that's available. So I thought this might be interesting to you in terms of all this stuff about whether the weather is changing or whether it isn't changing. Well, we're just having the worst weather ever up in Sutherland. We had a really nice period from around 2015, 2016, up until 2021, when it's just gone completely the opposite side. It's just been a real disaster. So is it El Nino? Is it bad weather? It used to be very nicely winter, summer, very little difference. Now it's kind of all split everywhere. So possibly we've seen an effect also in Sutherland. In terms of publications from SALT, we broke the record last year again, which is great. What does that mean? I'll tell you in a sec. Sorry, I thought I saw this slide. Anyway, what kind of papers are they? Well, by broad science categories, most of them are going to be stellar. And that's because generally stellar papers, these ones are focusing on our own galaxy. They're nearby, they're individual objects. So you kind of observe one and publish one, or observe one or two and publish one. Extragalactic papers tend to deal with the big questions. Where does the universe come from and all that stuff? So the stellar papers more concerned with the evolution of the stars. The extragalactic are dealing with the evolution of galaxies and the universe. And so they need long-term statistics because galaxies don't evolve in sensible timescales. And so it ends up being long surveys with statistical analysis. And so it takes a long time for those papers to come through.
Can I ask you a question now?
Sure.
This is about what you're saying, which is that previous slide you said that there's awful weather.
Yeah.
And yet the number of publications has increased.
So we take into account some of the weather and also publications take on average 2 years to come through. So we're only going to see the effects of COVID and the effects of, so I'm not expecting that to kind of continue up and up because between the weather and with the COVID, I suspect it's going to dip a little again. But yeah, it's partly because the weather was good, partly because we're getting better also, we're constantly improving the telescope. And also surveys that started a few years ago are now reaching completion and they get published. So it's a bit of a continuous curve. And then the supernovas and gravitational wave papers, they're just essentially one object, one paper. And so they also get quite a lot of publications because those are like time restricted. Those are your priority zeros. The supernova happens now. It's not going to wait until next week. You're going to observe it now or it's gone. Same with a gravitational wave or with objects that go bump. And we're doing optical identification of those. What is it that we just went bump? If you don't get it now, you'll never know. And there's nothing astronomers hate more than never knowing. How are we doing compared to other telescopes? So it's been more than 10 years now since SALT started. And so we can kind of start comparing ourselves to all the other big kids on the block. SALT is on the red curve at the bottom and also with filled circles for those of you that may have trouble with colors. So we're kind of on the lower side. We are more restricted and we have a smaller community of users, but we going on the similar trend to other telescopes of similar size around the world. So we're actually doing pretty well in terms of publication rates. And in terms of cost, SALT was built because of its fixed altitude. It saves a lot of costs and is also operated on a shoestring, which is something our bosses are very proud of, and I'm not so proud of. I wish we had a little bit more funding, which wouldn't harm that much the curves, but would give us a bit more money to play with. Anyway, it's very cost effective. So this is one slide. If any of you have like a lot of money out there and want to invest in something, we can take it. It's actually a very cost-effective telescope in terms of publications. But are we publishing the right things? And that's a question that's always at the back of everyone's minds. Oh, yeah, but you build a cheap telescope. Are you really doing impactful science? So it was really nice to get the Gemini librarian, so Gemini telescope one of them in the north and the other one in the south, but Iso Xiaoyat-san, he did an analysis on the impact according to how many citations various papers get. And this is mainly on ABJ, Astrophysical Journal, so it doesn't include all of the papers. But it gives you an idea of how the telescope publications in terms of impact compare to each other. And SALT is, that little peak, it's a yellow curve, for those who can see yellow and who can't, is that big peak in the middle, and then sort of follow the curve around. It's there with the others. It's not, the impact is good. We're doing the right things and we're creating good science. So our papers are good, even though we're a cheaper telescope. So that's nice to know as well.
What's this such a big spike?
That was the gravitational wave of 2017, because we got the first spectrum, first or second spectrum of that object. And then we got another one 2 days later. So we made it into the big, ginormous gravitational wave paper. And so that gets us a heck of a lot of citations in 1 year. So that's that paper pushed us to the top because, yeah, that was a gravitational wave target of opportunity. You're either there or you're not. And we were there. So it was quite an exciting time. So what else has been happening at the telescope? So as I mentioned just now, there are a lot of updates that have been happening. We're not just sitting there doing the same old. I like showing this because basically we do everything. We've just got everything, a little bit of everything. And so in terms of how we get to upgrade things, it sometimes has to be focused on specific what it is that we want to do, making sure that we don't break something else. So it has to be done carefully and making sure that everything works as well. So we added a new grating to our main workhorse spectrograph. So this one's the one that we use mostly in good weather and in dark moon. This one's the more sensitive. We gave it a new grating, and that adjusts much better to the size of the detector in December. And it's actually doing very well. We had to retire one of the gratings, but the users are actually really happy with the new one. So that's so far so good. We also identified in 2020 that we had the most horrible of things, scattered light in the detector, in the data we were taking with our dark night instrument. There's two components to this. One was internal to the instrument, and the other one, unfortunately, comes from the spherical aberration corrector. So that's the optics that sit at the bottom of the telescope, and they are really, really difficult to get to. So because they're so difficult to get to, there's a couple of mirrors that have not really been cleaned properly because they're really difficult to get to. So that one, I'll tell you a little bit more about plans, but for RSS, it was a no-brainer. We replaced the optics, and that's looking really good. So now the scattered light that comes from the detector itself is gone. Now we only have the SAC to fix the spherical aberration corrector. Also long slits. So these are the little light lines that you need to use to be able to do spectrographs. So ours are really old. And they were essentially engineering ones. These are the ones that you make at the beginning and you go, let's see how it goes. And let's see how it goes. It's now 2023, and we're still using those engineering masks that we used then. So we're really in desperate need of some new ones. We built some prototypes by various companies, and they did not actually meet quality controls. So that was quite disappointing. But we actually managed to use those prototypes to understand the gap between what the companies thought we wanted. So all of those engineering measurements that they need and what we astronomers see at the telescope. So we kind of used them as the Rosetta Stones. And it turns out, to our surprise, that the SAO workshop can do what we want them to do. Who knew? So we're now testing the new prototypes. And hopefully either this week coming or the week after, we'll be testing the new prototypes built here at the SAO, and I'm hoping that those are good ones. We get to keep them. More for RSS. So we're building, I'm sure you've heard of Maxi, or some people have. We're building a red arm at RSS. Why? Currently, the instrument can only look at one part of the spectrum. We're wanting to do the full optical spectrum in one go at a decent resolution, so that when you're doing identification of objects, you don't have to do it in two goes. You don't have to go the red part and then the blue part. This is a limitation of the spectrograph we currently have. And so we build in a second arm so that we kind of do both the blue and the red at the same time. So that gives us the full picture of what it is that we're looking at. And it's taken a little bit longer because now it's, but the PDR, the preliminary design review for this instrument is happening now in September. It is very tricky to do something like this on an instrument that's already working without upsetting anything. So this is why it's going slower than we thought it would at the beginning when it sounded so nice and simple. We're also getting new detectors. Our current detectors have 3 chips. So that means there's 2 chip gaps where there's no light. Whenever you take data from them, there's like a little gap, 2 gaps in between. These new detectors that we're getting are full monolithic detectors, so there will be no gaps. And again, that saves you having to do 2 exposures if you need to fill in the gaps. You need to take 2 exposures at different angles to fill in your gaps. So that will also save us. That should be arriving fairly soon, I hope. The detectors are already here. They just need to be put in the cryostat, software written, and then commissioned. So it's going to take probably until around this time next year, anticipating. And then another development happening here at the SAO workshop is what is called the SLITMAS IFU, integral field units. So these are like, I don't know how to explain it. So you have fibers, you put in optical fibers. So you have, instead of a camera, you have fibers acting like pixels, if you like. So you have a small, and then all of those fibers are then put through a spectrograph. So each one of those fibers gives you a full spectrum. So they're called integral field units, and most large telescopes around the world have them, so we want them too. They're good for extended objects, like galaxies or planetary nebulae, stuff that's kind of big. Yeah?
Are these relatively new things?
They've been around for a while.
Because it's the second time I've ever heard of them. And the first time was this afternoon at 3:30.
Really?
Yeah.
No, they've been around for a while. We've wanted them for a while, and the fiber lab is being developed specifically to build these. So they've been around for quite a few years now. And most telescopes now work on IFUs because you're no longer limited to a single slit. You can put your fiber bundle wherever you want, and then you're getting a spectrum of the whole thing in one go. You just need to know which fiber goes where, and then you can rebuild from where each spectrum comes from. It's great for galaxy, extragalactic work. It saves you having to move your slit to get this bit in that part of the galaxy. Now you do the whole thing. So, yeah.
Physically, what size of these fibers taking image?
So physically speaking, look, I actually have a slide now. This shows you the near infrared fibers. So it can tell you physical, does it tell you physical size? Does it tell you the physical size?
Like the megapixels per fiber.
Okay, yes. So these are the ones we're having built for the optical are similar size to the one that we're building for the infrared so that they match. So the idea is that they will match. So I'll show you a little bit now. But they're basically small. You need a massive detector if you have a lot of fibers or many detectors to put them on. But that comes with different problems. It's like using different chips. Now, cross-calibrating from different detectors is not fun. So most people try and keep it to a single detector.
Each fiber is standard color.
No, each fiber does a whole spectrum
Also,
of that area of sky that it's sitting at.
so you're getting about 1,000 copies of the same object.
Yes, but you're getting each one on each color. So you're measuring the intensity at each wavelength, if that makes sense. And then if you have 1,000 fibers, then you're getting 1,000 data points. So you could build an image back by summing up all of that. It's not high resolution because those fibers are all of them over an arc second in size. So you're not going to have high spatial resolution, but you will get this resolution the spectrograph gives you. So you're getting all of the light through. They're really cool. So we want them too.
So effectively, it's the light that is coming off the grating, the full spectrum of the grating that is then falling on this particular slit mask. And the individual fibers get the individual wavelengths and goes to the detector.
Yeah, so
the
you
light
have
separated before
the light comes in. So say a galaxy, the light comes in, then you straighten them and you put them through a slit, through a grating, and then they go onto a detector. And so all of them each fiber makes its own spectrum because each one is being dispersed. So then you get from this part of the galaxy, it has its own spectrum, and that part of the galaxy now has its own spectrum. So you can measure velocities and you can measure densities or whatever it is that you're interested, compositions, whatever you're interested, but it's all from one measurement. So they're very nifty. Did that make sense? So we're getting a few of these, and I think one of them we're hoping to test at the telescope before Christmas, if all goes well, in the optical. So for Her Royal Highness, the high resolution spectrograph, she's become the main workhorse instrument for when we have brighter moon, because for high resolution spectrograph, you're dispersing the light more, so you need bright objects. And for those, you really don't care what the conditions are. They're bright enough, and it doesn't really matter if the scene is poor or if you have bright moon. So it turns out to become a main workhorse. So what are we doing for her? We're getting a laser frequency comb. I don't know if you guys have heard of these, but they're also super cool. So this is the fiber fed. So it's a single fiber. It's because it's split into three so that it fits properly through. It's a bit like the IFU, but it's only a single fiber. They just cut into image slices into three. So this is the spectrum of the star coming along. And then it has a reference fiber that we can use to measure sky. But in this case, we put a calibration source so that we can measure wavelengths. And the bright lines, these ones here, are the regular calibration lamps we use. I don't know if you are familiar, but they tend to be an element or a combination of elements like copper, argon, xenon, neon to calibrate the wavelengths. So we put a light that we know where these wavelengths are, and then we use it to calibrate our image. So these are from our thorium argon lamp, these bright ones. And these little teeth are from a laser frequency comb. So that's a laser that is split, made into interference pattern. And it's so it comes at really well-defined wavelengths. And so if you're trying to measure velocities of exoplanets, you can't afford to use one line here and one line there, because you really need to mark the wavelengths really accurately to measure your velocities. And so for things like exoplanet work, this is going to be amazing. So the team are coming up now in August to begin. And we were hoping they were actually going to finish in August, but there's one component that hasn't arrived yet. There were delays. And so it's only arriving later in the year. And the team, because they're teaching at the university, then they're only coming back in in December. So we're hoping we will have it working before Christmas, but we're not too sure yet. Fingers crossed we do. But this thing is really amazing for exoplanet work, which is when the hard work starts. And then the new kid on the block, this is the real new kid on the block. It's our near-infrared spectrograph. So SALT so far has been an optical telescope up to 900 nanometers. NERWALS is extending the wavelength coverage to 1700 nanometers. So we're going now into the infrared. And for the telescope that's blue optimized, this is not small. It's also fiber fed. It's an IFU. So that also comes with its own challenges, but it's already at the telescope. This started commissioning in October 2022, so about last year, nearly a year ago now, and is some of the image does it like the footprint of the IFU on the, I think that was the Eagle Nebula, and then kind of you can see the trace from each fiber of the bright star in the Eagle Nebula. So this was just to see if it worked. There's not meant to be any science or anything, just basically shoot and see what you see. And there's a little map of where the fibers are. So it's all really very confusing where these fibers land. So the central part of the fibers, so the central part of the IFUs are landing on the edges, which is, it takes some getting used to. We're going to need some software to help the poor salt astronomers verify that we're getting what we think we're getting. But work in progress. There's been a few issues. There always are with a new instrument that's pushing what SALT can do with any instrument. But we've been having quite a lot of progress since then. So we now really started to take some science observations, preliminary commissioning science observations, determining what the instrument really can do. So hopefully we'll be on full operations towards the end of the year.
The mirror coatings are suitable, they were suitable for near infrared, given that modified coatings on the mirrors.
No, that's fine. They do transmit through the infrared. Yeah. And then this instrument is actually also in the basement. It's IFU fed, like HRS is down at the bottom. It is in a box. I can't remember the temperature is the fridge is at. Do you remember, Christian? But it's very cold temperatures to reduce all the thermal background. So the worst thing for near infrared is sky. Yeah. But at the telescope, it's open. In terms of some of the user software we've been doing. So Christian and his team have built a new SALT web manager. This is the software on the web that we astronomers use to look at proposals, evaluate proposals, to choose our observations, look up the finding charts and identify the objects we're supposed to be observing, make sure we're in the right place. So it's a lot faster and it's really cool. So that was long overdue. We also have a find a chart generator, because you tell astronomers that you need a find a chart, and some people right at the beginning of the project would give us hand-drawn maps of more or less what it looks like, which was a bit of a disaster when you're at the telescope and you're seeing 20 gazillion more things than they've drawn on their little hand-drawn chart. So we had to create a find a chart generator. So now we've got a new one updated that includes the new instrument, the near infrared. It has that little IFU footprint, so you know where you're putting your object. You know where to find the chart is, right? Just check in. Okay. We also have the ability now to submit your observing blocks, what it is that you want to do, or your full program if you really want to, like some objects. Some people have 200 objects they want to submit and they don't want to do them one by one. Using the, your GUI graphical user interface, that will take forever. So we now have a software that can actually submit all that programmatically. So it saves a lot of work for a lot of lazy astronomers like me. We have some Q simulation software also, because when you're prioritizing what to observe next on a very limited time, there's always like, should I do this one or should I do the next one, or do I have a gap or can I avoid the gap? So we have a Q simulation software that now investigates all of the options and gives us some idea of whether we should change some of our parameters to make sure that we're always doing the best we can with the time we have. So some of the parameters are, do you wait? If you have an upcoming priority 0 object coming up, should you go for a high priority object or do you wait? How long do you wait? Because you don't want to have the telescope idle, because that's time lost. Those photons have been traveling for millions of years and they got nowhere. So, that hurts. So it's always, which observation do I do first? Do I do this one or do I complete that program? Or so there's always many things that you can do in the same time. And there isn't a smooth minimum. There's never an optimal, this is the best queue there is. It's the best queue there is right now, because 5 minutes later, the sky has moved, source windows have changed, and so it's completely different. So it's important to have your right parameters so you can investigate long-term how you're doing, am I achieving what we said to do at the beginning? Because you're going on a night by night doing your observations, and at the end of the semester, you have to respond to all the users and say, this is how much we got for you. And you need to explain to them, well, I'm sorry I didn't do your observation because I had these other ones that jumped the queue because they had higher priority. Or yours were too difficult because they were too tight and I never saw them. So it happens. We call them the too tight tracks, the TTTs, Christian. So people, you have 3,000 seconds that your track is, how long you can sit on it, and they give you a block that's 3,000 seconds. So unless you happen to be on sky at that time, I will miss it. And so those were invisible. We didn't know what had happened to them. It took us a while to figure out what had happened. Learn. And then something else we really need is pipelines. So that's full data reduction pipelines, so that you don't just get that image like I showed you with these traces and kind of ugly looking images, but you actually get your spectrum reduced on your desk so that the astronomer in the morning doesn't have to do any processing. They just get the data and go, oh, I know what that is. Or, oh, this is good. Or, oh my gosh, I'm not seeing what I needed to see. Maybe you were on the wrong object, and then really happens. And then we have to retake the observation.
Is the data pre-filtered? If you take data, get hundreds of gigabytes or terabytes, is it being pre-filtered to a?
No, so what we do is actually we add on. So we take the data and then we process it, but we keep the raw. So all of our data products are added, so the astronomers can verify step by step how we got from the raw data. They can take whatever they want, whatever step they want, because a pipeline doesn't work for everyone. It depends on what you're looking for. If it's a stellar object and it's nice and easy, you will be fine with a pipeline. But if it happens to be a galaxy and it's got really nice faint wings, then the pipeline may not take the sky measurement in the right places. And so you will be incorrectly looking at what you're looking at. And so they need to verify that everything is done correctly for their science. So you can only do so much. So we plan to produce data products so that they can look at it, but they will still want to see step by step what's been done to the data to verify that they're seeing what they think they're seeing. Yeah. And in terms of the telescope, I'm going very quickly now. I mentioned the SAC, the spherical aberration corrector. The cleaning is the big problem. And so one of the things we're looking at is if we need to take that off to increase our throughput and get rid of our scattered light, can we do other things as well to improve? When we built SALT, we thought we were going to be using it in this way. And as we grew with it and we built and upgraded, we're working it differently from what we originally thought. So can we provide, for example, a common guidance to all of the instruments? Currently, every instrument has to have its own guider. Can we have one for everyone? Can we produce stable tip-tilt measurements so that everything is always in focus and not depending on the guider that you're using? Can we enable the simultaneous optical and near infrared, which was the original goal, But because the near infrared ended up in the basement, we can't do that right now. Can we add a dichroic? So we can, again, do both. So this is super scary, especially for a working telescope. Not very glamorous because no one wants to hear that you're redesigning something that's already working, but it could potentially really do a lot of good at the telescope. So we're scoping. The guys have been given carte blanche and they're coming up with really scary things that they could do and it would be so much better. We'll see what comes out of that, but it's potentially very exciting. And, you know, so the good, some not very exciting stuff happened also recently. We had our tracker had a problem with one of the hexapod legs and we didn't know. And it ended up, so we are pointing, so this is how good our pointing is. And it just kept going away from us. And then we would fix it and then it'd go away again. And then we would fix it and then it would go away again until it broke. No one could figure out where the problem was. I tell you, they went through that telescope up and down, left and right, and they couldn't figure it out. And it ended up being inside one of the hexapod legs, the ball bearing, required a whole big replacement. But for us, it also happened to come right at the end of the semester, when we just had a month off to do the RSS optics replacement. And so it just had the worst possible time, in dark time. Our QD was just, our completion starts last semester were ugly. It took us offline only for 10 days, thanks to heroes, the team in Sutherland and the team here in the workshop that did all the repairs to the parts they procured. And amazingly, actually, it also had an impact on IQ, on our image quality, on our seeing, how sharp we can see the stars. It also impacted the science. So some people are coming back now and saying, the data that I saw, it just doesn't, it's so much better now. The previous observation you took was not so good. And you can see it there in terms of comparing what we measure with the external seeing measurement and the internal from the guiders, what it was on a similar semester the previous year and this year. We could really see that we were doing really badly. We did work at it, we just couldn't find what the problem was until the tracker finally failed and put us out of our misery. And now it's working beautifully. And we're back on luckily. Sorry. And then I thought I'd share some science highlights, just a couple of the kind of things that SALT has been involved in kind of relatively recently. This one was 20 years of May, but last year. So it's we contributed through high resolution spectrograph to untangling the light curves of a very complex oscillating object. And it turned out to be a double binary, as it were. So there's those two stars, those two stars are orbiting each other, and those two stars are orbiting each other, and then the two groups are also orbiting around each other. And these systems, they're interesting because they are, quadrupole systems are not very stable. Even though they're relatively easy to form, they tend to form through mergers, and there's throwing, I don't know if you ever tried playing with dynamics, but they kind of go all over the place. So the stable ones are not so easy, but also because what the end point is, this is not a stable system, and the end point will most likely end up in merging, and it will most likely be on the Chandrasekhar limit. So it would end up as a potential 1A progenitor, supernova 1A, which are what's being used as the standard candles to measure essentially the size of the universe, the evolution of the universe. So we don't understand how we create supernova 1A, not really all the way, understand all of the channels that can generate supernovae 1A. And this is exciting because this is a system, one of the ways in which it could. This is shown not to be stable, and it's one of the ways that will potentially create supernova 1A, and it opens up another channel, another evolutionary path. So this one's...
How long before the move?
How long? I don't know. I actually-
They haven't counted.
I didn't look at that one. This is unfortunately, none of these are my science. So mine wasn't kind of exciting enough to make the cut. I couldn't kind of make it. So another very interesting salt contribution. Just everything is kind of comes from multiple multi-wavelength observations these days. So this is a super soft source, which is mostly a binary system. And it, again, going back to supernovae 1A and not understanding how they're generated. Supernovae 1A are mostly, they don't have hydrogen, they have helium. And it's kind of difficult. We do not find so many helium binaries that would eventually end up in a supernovae 1A. And it's possible that through studying, so this one's actually a helium supersoft source. There's only helium in the system. Its mass transfer is helium. And it's also seen that the growth of the white dwarf is slower than was expected, than it was believed it would be with the helium accretion. So it was growing slower, the accretion rate was slower, and yet it does, it has these outbursts. And so it will potentially eventually will merge and become a supernova 1A. And so this is yet another object that may provide another channel towards understanding these standard candles that no one really understands. And then moving away a little bit to one extragalactic, because that's more my side of things. So this one's the Peekaboo galaxy. It's called the Peekaboo because it's right next to a very bright star, which was right in front of it like 10 years ago. So now that it's a high promotion star, so now it's moved away, and now you can see it, the bright thing sort of underneath is the galaxy itself. And it happens to be very unusual because it's extremely metal poor. So through the understanding of galaxies is that in the first billion years or so, we got stars. After the Big Bang, we got stars. And then the stars evolved, they exploded, they threw heavier elements, they formed galaxies, and the galaxies contained old stars and contained heavier elements. And we call that metallicity increase. So all of the non-helium and hydrogen that's generated through supernova explosions and thrown into the galactic mediums is kind of increasing the metallicity. And this particular galaxy looks like it's only had stars in the last billion years or so. And the question is why? Does it have an old population that we do not currently see hidden in there somewhere? Or what happened? Why did this thing not start producing? So it's only doing it now, and it didn't do it then. What was the environment? So it helps us to try and understand the picture of, you have a general picture, and everything that's an outlier is interesting because it challenges you to understand how things really do work. The simple pictures very rarely are that simple. And so this is a very interesting object because of this lower metallicity, because we don't know where it fits and we don't yet understand it. It's one of the lowest metallicity galaxies and youngest galaxies. And it's nearby, which makes it very easy for us to get data from it because it's nice and bright. We can study it in detail and really look for those faint older populations of stars. So that was very interesting work. And this, one of the collaborators right at the end is Alexei Kniazev, which is one of my team members, was involved on the salt observations of this particular galaxy. And we're not the only ones that think this is an important galaxy. Right outside Somerset House in London, there is a sign that tells you where it is. Except don't look at the arrow. We know the arrow is wrong, but you know, the principle stands. It's just, it is an interesting object, and is worth following up. So just a summary. So SALT is our 10-meter class telescope, and it's available to all the partner institutions, which include all South Africans and African countries with collaborations. It's located in one of the darkest sites in the world, and it really is. We can prove it. We have had many projects recently completed, are on the go or near completion, both in terms of instrumentation for the telescope itself, in terms of software. We're doing pretty well. Our publication rate is good, and we are publishing the right papers, but at a much lower cost. And someone fix the weather, please. That's we really want better weather now. So thank you very much for listening.
Presentation. I'm sure that
You're welcome, Rory.
Molly Anthony was sitting here, she had to go, and she said it was really fascinating. Thank you very much. She's doing green electronics. She can see her future before.
Awesome. That sounds good.
Yeah.
Yes.
I see that Richard's hand is up. Richard, if you could just unmute yourself and ask.
Can you hear me okay now?
Perfect.
Okay, great. You were talking about spectrographs earlier and calibration lamps. Do you ever get an emission line or an emission or an absorption line that does not calibrate to any of the emission lamps or calibration lamps that you've got in anywhere in the world?
I'm not sure I'm understanding the question. Are you talking from a science, whether there are emission lines we haven't identified?
Yeah, that's correct, yes.
I think they generally, I mean, sometimes there are some mysterious lines because it may be that it's an object and we haven't identified the redshift, an extragalactic object. If you only have one emission line, it's very hard to pin a redshift. Generally, we do know what the lines are. Just sometimes if you haven't completely misidentified the object, then you not know where all of them are. Does that make sense?
If you're if you got a strong emission or absorption line and it didn't correspond to anything on Earth at all, is there a way of working out what it could possibly be?
Yes, so you could play with redshifts. You can, if it's absorption, sometimes it's things that are moving towards or away from you that will change the wavelength at which they appear, velocities of the emission or the absorption. So you could have outflows or inflows on your object, and that will also, or rotation, that will also give you shifts. So distance, if it's really far away and you've misidentified some of the, you don't know that it's far away, you would not identify what the lines are. But generally, if you don't know what the line is because you haven't quite understood what you're looking at, if that makes sense.
Yeah, that makes sense perfectly. Thank you.
Yeah.
Any other questions?
Yeah, I've got one. So where is the, you know, you're saying that salt is cheap. Please don't use that word.
Compared to other telescopes, we are good value, cost effective. You're right. Cost effective.
So say if you really need some funding to develop a new or whatever, where does the funding come from?
For SALT. So each of the partners contributes to the operations cost, and they also contribute to development. There's a development fund that they contribute to, and from those pockets is where funding for things like the top end redesign. So it's in the scoping phase, you need to hire someone to look into the scope and decide what could happen and what doesn't. So that comes from the development fund.
So it's what you're saying, that the development fund isn't big enough, or it's never big enough because, you know.
It's never big enough. But there's, I mean, some of the partners do have donors that contribute their costs, or they may contribute an instrument or part of an instrument or something. Some partners do have access to donors. Also.
If no one else saw, I just have a small question, which is if you show that graph of all the papers in the telescopes, the hobby everywhere, the head, which is the one that's on the bottom, but that was quite low down.
So Hobby Ebony, it has a similar issue to Salt in that they've got a small community, but they've got an even smaller community than we do. So they kind of reach their steady state very early on because of that. So now they also went offline for a while and they redid the whole thing and they're doing pretty well now. So I'm expecting that should start coming up because most of the work is extragalactic. So I expect most of it will start picking up soon as well. But they have a smaller community of users than we do. So much work people can do. Yeah.
What is the light pollution in Sutherland? Has it increased? Cape Town's halo already?
No, you can't see Cape Town's halo, not yet. It's protected by the AGA Act. So the skies in Sutherland are protected for that same reason, because we really need to protect the sky. So to be able to do anything that involves light in the protected area, it requires applying and getting permits. The latest developments, which are good in terms of having energy, is those what they call windmills.
Yeah. Yeah.
What's the word?
Farm.
Wind farms. Yes, the wind farms. Unfortunately, by law, they have to have a red light on top. And so we've been working with the wind farms to make them those lights so that they only come on when the radar detects that there's a plane nearby, and the rest of the time turn them off. So they're looking into doing all of that. And then if they're too close, they may not be able to go so close to Sutherland. So mostly it's well protected in that area. No, you can't see Cape Town, but you can see Sutherland. And we're hoping that the Sutherland municipality will bring down those much more directed lights.
Yeah, I think there is an astronomical act.
Yeah. Yeah, so all that area is protected from mining, for dust pollution, is from all the light sources as well, light pollution. And I don't know if fracking went into that, but I think the latest amendment does include the exclusion of fracking. So it does not allow within the protected area, which for fracking is a bit too close, but so.